Imagine you're sitting in an emergency room. You've got this really tight, heavy pressure in your chest.
Oh, man. That's a terrifying scenario.
Right. It's awful. And the doctors rush you in. They hook you up to all the machines. They take the scans. And then
You just wait.
exactly. Someone tells you that you'll have to wait like a week or two for a specialist to actually look at those scans and tell you if your heart is failing.
Which sounds like a total logistical nightmare. But in a lot of places, I mean, that is simply the reality of modern medicine.
It is a totally terrifying reality. Because usually, when we talk about medical diagnoses, we think of it like engineering.
Yeah, like it's a simple mechanical problem.
Right. You break your arm, the x-ray shows a jagged white line, the doctor points to it and says, there it is. It's visible, it's binary, and honestly, it's kind of comforting.
But the heart is not a bone.
No, it's not. When you step into the world of cardiology, that simplicity just vanishes entirely. And you have to remember, cardiovascular disease is the leading cause of global mortality right now.
Yeah, we are talking about over 20 million lives taken annually. It's staggering.
It really is. But as you dig into the research we're exploring today, you realize the real bottleneck in treating this massive crisis isn't just the disease itself.
No, the real bottleneck is the human interpretation. We're dealing with these intensely complex, multi-layered cardiac tests, and, well, the human brain can only process that information so fast.
And we simply do not have enough human brains to do it.
Yeah.
I mean, get this. A staggering near half of all U.S. counties lack a single practicing cardiologist.
Wait, half?
Half of them. So if you're living in one of those counties and your heart is doing something strange, you are waiting. And in cardiology, waiting is the absolute enemy.
Which is exactly why the source material we are exploring today is just so critical.
Yeah, tell them what we're looking at.
We're looking at a groundbreaking new paper out of Stanford detailing an artificial intelligence system called MARCUS.
MARCUS, right?
Right. It stands for Multimodal Autonomous Reasoning and Chat for Ultrasound and Signals.
It's quite a mouthful. But our mission for this deep dive is to really unpack how MARCUS completely changes the game.
Oh, it's a massive shift.
We're going to explore how it moves past the glaring limitations of the AI models you might already be familiar with, how it cures this truly terrifying AI hallucination phenomenon called mirage reasoning.
Which we will definitely get into because that part is wild.
It is wild. And finally, how it provides near-instant, expert-level cardiac diagnoses.
And to really grasp why MARCUS is such a massive leap forward, we kind of have to start by understanding why the incredibly smart AIs we already have are fundamentally failing in the cardiology department.
Okay, let's unpack this, because I know a lot of you listening are probably wondering, wait a second, haven't we already seen headlines about ChatGPT and Gemini passing medical board exams?
Oh, sure. They passed them with flying colors.
Right. But I like to compare those current frontier models, the really big famous ones, to like brilliant top-of-their-class medical students who have memorized literally every single textbook in the library.
Okay, I see where you're going with this.
But they've never actually looked at a real, messy, breathing human patient.
That analogy hits the nail on the head. Because let's look at what actually happens in a clinic. Right now, human interpretation of raw cardiac data is painstakingly slow.
How slow are we talking?
Well, a highly trained expert needs 3 to 5 minutes just to read a standard ECG. The squiggly lines on the paper.
Okay, 3 to 5 minutes doesn't sound too bad.
Sure, but then they need about 20 minutes to interpret an echocardiogram, which is essentially a live ultrasound video of your heart pumping.
Oh, wow.
And if you need a cardiac MRI, a CMR, that takes over 30 minutes for a specialist to review.
Jeez. And when you multiply that by dozens of patients a day, the backlog just becomes completely insurmountable. The doctors are exhausted.
Exactly. So naturally, researchers tried to apply artificial intelligence to speed this up. And I mean, we've seen some progress.
Right, there were earlier models.
Yeah, previous Vanguard systems, like one called 𝗫𝗫, did a great job at upskilling general practitioners. But systems like that are essentially text-only reasoning engines.
Text-only, meaning what? They don't see the pictures?
Right. They rely on a human doctor to look at the visual scan, write down what they see in text, and then feed that text paragraph to the AI. The AI itself is completely blind to the raw physiological data.
But hold on, we do have some AI that looks at the actual medical scans, right? The source material mentions models like EchoNext or EchoPrime.
We do. And they are fantastic at their specific jobs. I mean, EchoNext looks directly at raw ECG waveforms. EchoPrime digests those echocardiogram videos.
So what's the problem?
They hit what the researchers call a single-modality ceiling, meaning EchoNext only understands the electrical signals of an ECG. EchoPrime only understands the video of an ultrasound.
Ah, I get it. They're trapped in their own little silos.
Exactly. They can't cross-reference.
And clinical cardiologists don't work in silos. If you go to the hospital, they don't just look at one test. They use multimodal data.
Right. They look at the whole picture.
They look at the electrical signals and the ultrasound video and the MRI, and they synthesize all of it together to figure out what's wrong with you.
Which raises an important question. Why can't we just use the big general frontier models like a GPT-5 to look at all these different types of scans at once?
Because they can look at images now.
They can, but the paper explains that when you try to do that with medical scans, the models kind of fall apart. They suffer from what the authors call data illiteracy.
Data illiteracy. That's an interesting phrase.
It is. It happens because those massive models are trained primarily on internet data. They scrape the web for text and standard images.
Like pictures of cats and bicycles.
Exactly. They are fundamentally shielded from the high-fidelity, longitudinal, messy hospital data that actually teaches a human doctor how to diagnose a nuanced heart condition.
Well, yeah. The internet doesn't just have a public database of 13 million raw, uncompressed cardiac MRIs just sitting around for an AI to practice on.
No, definitely not. But hospitals do.
And that takes us directly to Marcus. If single-focus AIs and internet-trained language models aren't enough to solve this crisis, how exactly is Marcus built differently to handle the raw reality of cardiac data?
It really comes down to two major factors: the training data and the architectural design. First, the data. Marcus was trained on a staggering 13.5 million clinical images.
13.5 million. That is wow.
Yeah. To break that down, we're talking about 250,000 ECGs, over 1.2 million echocardiogram images, and over 12 million CMR images.
That's a mountain of data.
It is. But having a mountain of data isn't enough. The real genius is the structure. Marcus employs a hierarchical agentic architecture.
Okay, wait, I need to push back here. Why make it hierarchical?
What do you mean?
Well, if you have 13.5 million images, why not just build one giant AI brain, dump all the text, video, and electrical signals into it, and let it figure it all out at once, like we do with the other big models?
Well, that is exactly what standard models try to do. They try to map all of those different inputs into a single, massive mathematical landscape called a visual embedding space.
Okay.
But the developers of Marcus realized that doing so leads to something called attention dilution.
Attention dilution. So is that like trying to listen to 3 different audiobooks at the exact same time?
That's a great way to put it, actually.
Like you hear a lot of noise, but your brain can't actually comprehend any of the individual stories because everything is competing for your focus.
That is a perfect way to visualize it. The model just gets completely overwhelmed by the sheer volume of competing data types.
So how does Marcus fix that?
Instead of doing that, Marcus is built like a medical board.
Oh, I like that.
Yeah, you don't have one doctor trying to do everything simultaneously. You have an ECG expert AI, an echo expert AI, and an MRI expert AI. They each focus solely on their specialty.
Okay, so they're individual agents.
Right, and they all report to a chief orchestrator AI.
I really love this boardroom analogy. It feels so much more intuitive than just a giant black box. But how do they actually talk to each other?
Well, what's fascinating here is that these subagents don't use a complex shared mathematical code to communicate. They use plain natural language.
Wait, really? Just normal words?
Literally. The orchestrator AI talks to the ECG expert in English, asking, "Is low voltage present?" And the ECG expert replies in English.
But why? Why is plain English better than some super efficient computer code? That seems backward for AI.
Because it completely future-proofs the model.
Oh, I see.
Yeah, AI is moving incredibly fast. If a brand new, incredibly smart language model comes out next year, you don't have to retrain your entire visual system from scratch to make the new model compatible with some shared mathematical space.
You just swap the boss out.
Exactly. You just plug the new language model into the orchestrator role, and it can immediately start managing your visual experts because they all already speak English.
Okay, that is remarkably clever engineering. But, a clever architecture is only great in theory. We need to know how this virtual medical board performs. When a highly complex patient actually walks through the door, does this team approach actually yield better results?
The proof is absolutely in the data, and honestly, the margins aren't even close.
I have the stats in front of me right now, and they are wild. So the researchers tested the models on complex multimodal cases.
Meaning situations where you absolutely have to look at the ECG, the echo, and the MRI together to get the right answer.
Right. And GPT-5 thinking scored 22.5% accuracy. Gemini 2.5 Pro Deep Think scored 27.5%, and Marcus,
Let's hear it.
it achieved a staggering 70% accuracy.
Yep.
It almost tripled the performance of the best general AI models in the world. That's insane.
It is. And if we connect this to the bigger clinical picture, it shows exactly why that agentic orchestrator is so vital. Let's look at a specific, highly difficult clinical example from the paper.
Okay, lay it on me.
Distinguishing between constrictive pericarditis and restrictive cardiomyopathy.
Okay, stop right there.
Too much jargon.
Those sound incredibly intimidating. Break those down for us, because without a medical degree, those just sound like random Latin words.
Fair enough. Fair enough. Both conditions basically mean the heart is having trouble filling with blood, which causes heart failure.
Okay, bad news either way.
Bad news either way. But the underlying reasons are entirely different. In restrictive cardiomyopathy, the actual muscle of the heart has become stiff and rigid.
Stiff muscle. Got it.
But in constrictive pericarditis, the muscle is fine, but the protective sac surrounding the heart, the pericardium, has become thick and calcified, trapping the heart like a tight cage.
So one's a stiff muscle, and the other's a tight cage around the muscle. That sounds like a crucial difference.
It is, because the treatments are completely different. If it's the cage, a surgeon can cut the sac open and relieve the pressure. If it's the muscle, surgery won't help. And they are notoriously tricky to tell apart. So let's say a patient comes in. The echocardiogram video shows biatrial enlargement, meaning the top chambers of the heart are stretched out, and it shows what's called a septal bounce.
A septal bounce is a piece of the heart literally bouncing on the ultrasound?
Essentially, yes. The septum is the walls separating the left and right sides of the heart. Because of the weird pressure dynamics from that tight cage, the wall literally shudders or bounces back and forth when the heart beats.
Got it. Visually bouncing. What's next?
Next, the MRI shows pericardial thickening, that thick sac we talked about, and a lack of late gadolinium enhancement.
Okay, another big term. Gadolinium. What is that?
Oh, right. Gadolinium is a contrast dye they inject into your veins during an MRI. It tends to stick to scarred, damaged heart muscle. So a lack of it means the heart muscle itself isn't scarred.
So the muscle is fine, but the sac is thick.
Precisely. And finally, what does the ECG show? The ECG shows low voltage, meaning the electrical signals look unusually small or weak on the paper.
Because the cage is muffling it.
Exactly, because that thick sac is muffling the electrical current.
All right, so you have 3 highly specific clues from 3 different machines. When you feed all that raw data into standard frontier models, what happens?
They experience that attention dilution we talked about. They see the bouncing wall, the dye results, the electrical signals all mixed together, and they just panic.
They just guess.
Pretty much. They tend to default to whatever the loudest, most obvious single feature is in their training data, and they completely ignore the subtle context of the other tests. They guess wrong.
But 𝗫𝗫𝗏 doesn't panic.
No, it doesn't.
Because the orchestrator intentionally breaks the problem down into manageable subroutines. It says, okay, ignore everything else for a second. Query ECG expert. What do the electrical signals show? Okay, got it. Now, query echo expert. What's the structural movement looking like?
Exactly. It synthesizes the data the exact way a human cardiologist would, building a unified clinical picture from fragmented pieces.
And that deliberate step-by-step synthesis is exactly why it hits that 70% accuracy mark where the general models completely fail.
Right. It's the workflow that saves it.
So Mark said is incredibly accurate. But in the medical field, being accurate most of the time isn't really enough, is it? We need absolute trust.
Oh, absolutely. The stakes are literal life and death.
Right. So what happens when these models don't know the answer? Do they admit they don't know, or do they just guess?
And this brings us to a massive critical vulnerability in modern artificial intelligence.
Here's where it gets really interesting. Because the paper introduces this concept called mirage reasoning. And honestly, it is terrifying.
It really is.
For those listening, mirage reasoning is a phenomenon where these highly advanced AI models spit out complex, incredibly confident medical diagnoses based purely on the text prompt, while completely ignoring or hallucinating the actual medical images you provided.
It creates this perfect illusion of visual understanding. The model will sound like it is reading your patient's scan flawlessly. It will use all the right terminology.
But it's faking it.
Totally faking it. It's actually just making a very educated text-based guess based on statistics. In fact, it would give you the exact same confident diagnosis even if you uploaded a picture of a blank white square instead of a heart.
Which is an absolute deal breaker for a hospital. A doctor has to know beyond a shadow of a doubt that the AI is actually looking at their patient's unique heart.
Right. Otherwise, it's just a really smart autocomplete.
Exactly. So did Marcus solve this? Because reading through the data, the paper admits that in isolation, Marcus's individual experts actually fell for this trap.
They did. When the researchers tested them alone, the ECG, echo, and CMR expert models exhibited mirage rates between 33% and 38.5%.
Wow.
Yeah, that perfectly matches the dangerous failure rates of the big frontier models.
So Marcus is just as vulnerable to hallucinating.
Well, the individual experts are vulnerable, yes.
Oh.
But this is where the orchestrator AI steps in to save the day with a built-in defense mechanism called counterfactual probing.
Counterfactual probing. Okay, how does that work?
Remember how the orchestrator acts as the chief of the medical board?
Yeah.
When it asks the echo expert for a diagnosis, it secretly tests its own agent. First, it asks for the diagnosis while providing the ultrasound video. But then, entirely behind the scenes, it asks the exact same question again, but it removes the video.
Wait, it's essentially running an internal sting operation on its own doctors?
That's exactly what it is.
Like a paranoid hospital administrator. But hold on, let me challenge this. If you take the video away, shouldn't a smart AI just say, hey, there's no video here, I can't answer that? How does tricking it actually prove it's hallucinating?
You would think it would say that. That's the logical human response. But an AI experiencing a mirage doesn't do that.
It doesn't.
No, because it wasn't actually relying on the image in the first place. It just confidently keeps talking and gives a diagnosis based purely on the text prompt.
Wow.
Exactly. It completely exposes itself. So if the echo expert gives a highly detailed, confident diagnosis when it has the image, but then it gives the exact same detailed diagnosis when the image is suddenly missing, the orchestrator instantly knows the expert is hallucinating.
Because the answer should have changed.
Right. It flags that response as a mirage and throws it out. It only trusts the expert if the answer meaningfully degrades or changes when the visual evidence is removed.
Enforcing visual grounding by proving the image actually matters to the answer.
Yeah.
That is so simple, but so effective. And the result of this sting operation.
After implementing this counterfactual probing, 𝗏𝗏𝗏𝗏's mirage rate drops to a perfect 0%.
0. That is the kind of rock-solid trust you need in a clinical setting.
It's a huge milestone. It proves that hallucination isn't some unsolvable, fatal flaw in AI architecture. You just need a system that has the ability to verify its own work before it speaks to the user.
Okay, so we have a system that synthesizes multiple complex tests like a human. It's very impressive. But a 0% mirage rate at Stanford University is one thing. AI is notorious for failing the moment you move it to a different hospital.
Oh, the generalization problem, yeah.
Right. Different machines, different lighting, different patient demographics. AI usually breaks. Does Marcius survive the real world?
That is the ultimate test of any medical AI. So the researchers took Marcius and validated it on an entirely external group of patients at UCSF.
A totally different hospital system.
Different scanner vendors, different imaging protocols, different patient populations, the works. And for the ECG and CMR data, performance held rock steady. Accuracy stayed beautifully consistent between 87 and 91% for ECG and 85 to 88% for CMR.
That's great. But there was an anomaly with the echocardiogram data.
No was, and it's a fascinating one. For the echocardiograms, Marcia's accuracy didn't just hold steady, it actually jumped. It went from 67.4% accuracy at Stanford to 86.0% at UCSF.
Wait, it got significantly better at a hospital it had never even seen before. How does that work? It doesn't make sense.
It's unusual, but it suggests something profound about what Marcus actually learned during its training. Often, a medical AI will overfit to its home institution.
Meaning what?
Basically, it learns to recognize the exact background noise or the specific pixel artifacts of a Stanford ultrasound machine rather than learning what a sick heart looks like.
Ah, like it memorizes the camera, not the patient.
Exactly. But this jump in accuracy suggests Marcus's visual encoders actually learned the invariant underlying biological features of human cardiology.
It learned how to read a heart, not just how to read a Stanford camera setting.
Precisely. Its clinical knowledge generalized perfectly across hospital systems, whereas the general frontier models it was compared against, they flatlined at around 35 to 50% accuracy no matter where they were tested.
Okay, I have to play devil's advocate here. It sounds too good to be true. So where does this virtual medical board fall flat? What is it bad at?
Well, it is definitely not perfect, and to their credit, the source material is highly transparent about its current limitations.
Okay, what's the catch?
If you ask Marcus to identify a pathology or an arrhythmia, say, is there a block in the electrical signal? Or is this valve leaking? It crushes it. It scores up to 4.5 and 5.0 out of 5 on the expert greeting scales.
Yeah.
But if you ask it for precise, continuous quantitative measurements, for example, calculate the exact ejection fraction percentage, or measure the precise thickness of this ventricular wall in millimeters, it struggles immensely. Its score drops to around 1.76.
So it's great at telling you what is wrong, but not exactly how many millimeters wrong it is.
Right.
Why is that, though? If you can see a leaking valve, why can't it just measure it?
This raises an important question about how vision language models actually see. These models are incredible at recognizing broad patterns, like the shape of a sick heart or a bouncing septum.
Okay.
But they do not have a built-in spatial grid to count exact pixels or calculate geometric millimeters. Think of it like asking a poet to guess the exact square footage of a room. Yeah. The poet can tell you the room feels cramped, they can describe the claustrophobia perfectly, but they can't give you the architectural math.
That makes total sense. They are pattern recognizers, not digital rulers.
Correct. And to be fair, the big frontier models like GPT-5 also failed miserably at this exact task. It proves that pulling precise numerical measurements from raw visual imaging is a shared hurdle for all current vision language AI. It is the next frontier they will have to conquer.
So what does this all mean? We have covered a massive amount of ground today. We started with a global medical system that is fundamentally bottlenecked by human limitations, too much complex data, and nowhere near enough cardiologists to read it.
Right. And we've seen how a system like Marcius offers a genuinely scalable solution. By using an agentic architecture, a virtual medical board communicating in natural language, it breaks through the silos of single-modality AI.
It brings together the electrical data, the ultrasound, and the MRI, synthesizing it all without falling victim to that terrifying mirage reasoning. It literally runs sting operations on itself to ensure visual grounding.
Which is still my favorite part of the whole paper.
Same. And it is providing specialist-level assessments that generalize beautifully across entirely different hospital systems. I mean, this isn't just a shiny new tech toy for Silicon Valley.
Not at all.
This is a tool capable of providing life-saving diagnostic access to that half of the country, and really, the world that currently has zero access to specialized cardiac care.
It really is a paradigm shift, and honestly, it leaves us with something much deeper to consider.
What's up?
Well, if we are truly entering an era where systems like Marcus can near instantly synthesize multimodal data, where the AI can entirely self-correct for visual hallucinations and deliver a complex diagnosis faster and perhaps more accurately, then the role of the human cardiologist in the next decade shift entirely away from the mechanics of diagnosis.
Oh, wow.
Think about it. If the machine can flawlessly read the scan, does the human physician's role evolve to focus purely on the empathy, the ethical navigation of treatment, and the profound human connection of patient care?
That is a wild, heavy thought. If the machine becomes the ultimate diagnostician, what does it actually mean to be a doctor in the 21st century?
Exactly.
We are going to leave you to chew on that one. Thank you so much for joining us for another deep dive. Keep questioning, keep learning, and we'll catch you next time.